Hello and welcome everyone. I'm Harshit Kanchav, Assistant Professor at Lloyd Institute of Management and Technology, and today we are going to deep dive into the world of sympathomimetic drugs, a class of drugs that mimics the action of sympathetic nervous system. In this session, we will explore the classification of sympathomimetic drugs, the synthetic pathway of two important examples, that is phenylephrine and salbutamol, and their structural activity relationship SAR, to understand how chemical structure influences pharmacological activity. Let us start with the classification of sympathomimetic drugs. The sympathetic nervous system prepares the body for flight and fight responses, increasing heart rate, dilating bronchi, raising blood pressure, etc. Sympathomimetic drugs activates this system by acting on adrenergic receptors. These receptors are mainly classified into alpha receptors, that is alpha 1 and alpha 2, beta receptor, that is beta 1, beta 2 and beta 3. Now, based on how these drugs exert their action, we classify them as follows. These the directly acting sympathomimetic drugs. These agents directly stimulates adrenergic receptors. Examples are adrenaline, noradrenaline, phenylephrine, and isoproterenol. Adrenaline stimulate both alpha and beta receptor, whereas noradrenaline primarily act on alpha 1 and beta 1 receptors. Phenylephrine selectively alpha 1 agonist used as a nasal decongestant. Isoproterenol non-selectively beta agonist increasing heart rate and dilate bronchi. These drugs are often used in emergency medicine to treat hypotension, cardiac arrest, and asthma. The second class is directly acting sympathomimetic drugs. These drugs do not directly bind with the receptor, instead, they increasing concentration of endogenous catecholamines like norepinephrine, etc., by promoting their release, inhibiting their reuptake, or preventing their degradation. The example of this class is amphetamine, that is CNS stimulant increasing norepinephrine and dopamine release, and tyramine found in food like cheese and wine increasing norepinephrine release. The next class is mixed acting sympathomimetic agent. These drugs work both ways, they stimulate receptor and promote norepinephrine release. The example is ephedrine. Ephedrine is used for asthma and as a stimulant of and their stimulant act on alpha and beta receptor and also promotes norepinephrine release. Based on the receptor selectivity, these drugs are divided into alpha 1 agonist, alpha 2 agonist, beta 1 agonist, beta 2 agonist, and beta 3 agonist. Alpha 1 agonists are mainly function as vasoconstrictor, example is phenylephrine. Alpha 2 agonist is reduce sympathetic outflow, example is clonidine. Beta 1 agonist increase heart rate and contractility, example is dobutamine. Beta 2 agonist is cause bronchodilation, example is salbutamol and terbutaline. And lastly, beta 3 agonist involves in lipolysis and bladder relaxation, example is mirabegron. Understanding this classification is crucial for designing and choosing the right therapeutic agent. Lastly, these drugs are divided according to the chemical nature into two types, that is catecholamines and non-catecholamines moieties. Catecholamines have catechol nucleus in their respective structure. Example is adrenaline, noradrenaline, and non-catecholamine derivatives do not have catechol nucleus in their respective structure. Example is ephedrine. As you see, the catechol nucleus is designed when you put hydroxyl group on the phenol moiety. So let us now explore the synthetic pathway of phenylephrine, a widely used alpha 1 receptor agonist. So the starting material is phenol. Phenol here reacts with chloroacetyl chloride, and this acetyl chloroacetyl group is transferred onto the meta position of phenol and by removing HCl moiety and converting it into meta-hydroxyphenyl acetyl chloride. This meta-hydroxyphenyl acetyl chloride further go amination or transfer of methyl amino group onto their acetyl group by removing HCl moiety from their site and transfer whole methyl amino group onto the acetyl moiety. Afterwards, this beta ketone group is converted into hydroxyl group by MPV reduction. On reducing, this ketone group is converting into hydroxyl group and the phenylephrine moiety is ready. This phenyl moiety is converted into L isomer by resolving with decamphoric acid. This phenylephrine differ from adrenaline only by lacking the fourth hydroxyl group on the benzene ring. The mechanism of action is this phenylephrine is selectively direct acting as alpha receptor agonist, have no effect on beta receptors, and it is work as a potent vasoconstrictor but less potent than epinephrine. This activates the alpha receptor causes the vasoconstriction of the arterioles. So primarily it is used in nasal decongestion. It is metabolized by MAO, that is monoamino oxidase enzyme, and it lacks catechol moiety, hence not metabolized by COMT, that is catechol O methyltransferase enzyme. I've already discussed the uses of this phenylephrine, that it is mainly used in relieving the nasal congestion and as a mydriatics. It is also used to prolong the action of local anesthetics. The basic adverse effect of this drug is skin rashes, itchiness, dizziness, light headache and high BP. अगर मैं सिंपल वर्ड्स में आपको बताऊं फिनाइलएफ्रिन की सिंथेसिस, तो यहाँ पे आप लोग देख रहे होंगे फिनॉल मोइटी रिएक्ट करती है विद क्लोरो एसिटाइल क्लोराइड। यहाँ पे एसिटाइल ग्रुप क्या है, COCH2, एंड क्लोरो एसिटाइल ग्रुप इज COCH2Cl। यहाँ हम लोग एक और मोइटी क्लोरो मोइटी ऐड कर रहे हैं, इसलिए ये कंप्लीट न्यू जो हमारा ग्रुप है वो हो जाएगा क्लोरो एसिटाइल क्लोराइड। ये क्लोरो एसिटाइल ग्रुप जो है हमारे फिनॉल मोइटी के मेटा पोजीशन पे इंटरेक्ट करेगा और यहाँ से HCl रिमूव आउट करके ये पूरा क्लोरो एसिटाइल ग्रुप यहाँ पे अटैच हो जाएगा और बना देगा हमारा मेटा हाइड्रोक्सी फिनाइल एसिटाइल क्लोराइड। इसके बाद यहाँ पे मिथाइल अमीनो ग्रुप से रिएक्शन हो रही है, आप लोग देख रहे हैं दिस मिथाइल अमीनो ग्रुप ट्रांसफर मिथाइल अमीनो टू दिस मोइटी टू दिस एसिटाइल ग्रुप बाय रिप्लेसिंग दिस क्लोरो ग्रुप। ओके, सो ये क्लोरो ग्रुप हमारा अमीनो ग्रुप के हाइड्रोजन और यहाँ पे Cl HCl बना के रिमूव आउट होगा और ये पूरा का पूरा ग्रुप यहाँ पे अटैच हो जाएगा। अब अगर हम फिनाइलएफ्रिन का स्ट्रक्चर देखें तो जो बीटा कार्बन है, अब यहाँ बीटा कार्बन हम कैसे समझेंगे, जो अमीनो ग्रुप के एडजेसेंट वाला कार्बन है, दिस कार्बन इज अल्फा कार्बन, नेक्स्ट कार्बन इज बीटा कार्बन। सो यहाँ पे बात हो रही है कि बीटा कार्बन पे हाइड्रोक्सिल ग्रुप है, बट अगर हम लोग इस स्ट्रक्चर को देखें तो यहाँ पे हमारा कीटोन मोइटी प्लेस्ड है। इस कीटोन मोइटी को हाइड्रोक्सिल ग्रुप में कन्वर्ट करने के लिए हम लोग यहाँ पे एमपीवी रिडक्शन कर रहे हैं। ओके, रिडक्शन में क्या होगा, ये कीटोन ग्रुप हमारा हाइड्रोक्सिल ग्रुप में कन्वर्ट हो जाएगा और हमें फिनाइलएफ्रिन जो है हमारा न्यूक्लियस वो कंप्लीट मिल जाएगा। ये है हमारी सिंपल तरीके से फिनाइलएफ्रिन की सिंथेसिस। नाउ लेट्स मूव टू द सिंथेसिस ऑफ साल्बुटामॉल। So the starting material for the synthesis of salbutamol is 2-hydroxymethylphenol, which on reacting with chloroacetyl chloride converts into 4-hydroxy 3-hydroxymethylphenyl acetyl chloride. Here we see that this chloroacetyl chloride transfer its chloroacetyl group onto the 2-hydroxymethylphenol. Afterwards, this 4-hydroxy 3-hydroxymethyl phenyl acetyl chloride is treated with tertiary butyl amine group and which displays this tertiary butyl group onto the acetyl group, and afterwards the beta ketone group is converted into hydroxyl group by MPV reduction and give salbutamol moiety. This salbutamol is beta 2 adrenergic agonist, and this activity is generally is because of tertiary butyl group which is placed on amino moiety. So it provides the bulkiness to the salbutamol, which influence the beta receptor selectivity. The mode of action is just it stimulates beta 2 adrenergic receptor, which are predominantly receptor in bronchial smooth muscles. Beta 2 receptor of smooth muscle activates adenyl cyclase, which increases cyclic AMP, and smooth muscles relax, which will directly target to the bronchodilation. The metabolism of this salbutamol is hydrolyzed by esterase enzyme in tissues and also conjugatively metabolized to salbutamol 4-O sulfate and by oxidative deamination. The major use of salbutamol is in COPD and asthma. The basic adverse effects are headache, palpitation, and trembling. So let us now moving towards the structural activity relationship of sympathomimetic drugs. If we see the structure of this adrenergic drugs, it contains a phenyl moiety along with the amino group which is separated by a ethylene bridge. If we modify the phenyl moiety of this structure, it will affect the mechanism of action, the receptor selectivity, but also influence the absorption, oral activity, metabolism, and the duration of action. For the direct acting sympathomimetic amines, maximal activity is seen in beta phenylethylamine derivatives, which contains catechol moiety and OH group on the beta carbon of the side chain. So, one by one, we discuss about the basic structure modification in the catecholamines or in beta receptor agonists. Or basically, we just say that the adrenergic agonist. High adrenergic activity occurs when the aromatic ring and amino group is separated by two carbon atoms. The primary and secondary amines have good adrenergic activity, whereas tertiary amines and quaternary ammonium ions or salts do not have very good adrenergic activities. The nature of amino substituents also affects the receptor selectivity of the compound. As the size of nitrogen substitution increases, alpha receptor agonist activity generally decreases, whereas beta receptor agonistic activity increases. As we see in salbutamol. Salbutamol contains tertiary butyl group on the amino atom, so their beta selectivity increases. So if we put the larger substitution on the amino nitrogen, the beta selectivity increases. Substitution by small alkyl group at alpha carbon, example CH3 or C2H5, that is methyl or ethyl groups, slows the metabolism by MAO, that is monoamino oxidase. So addition of small alkyl groups increases the resistance to metabolism and lipophilicity. So such compounds often exhibit enhanced oral effectiveness and greater CNS activity than other compounds that do not have the alpha alkyl groups. Substitution on beta carbon by hydroxyl greatly enhance agonistic activity at both alpha and beta receptors. So this beta hydroxyl group is generally essential for the activity, for the adrenergic agonistic activity. The compound with 3,4 dihydroxy group, which forms catechol moiety in phenyl nucleus, acting as direct acting drugs, whereas without catechol nucleus they act as indirectly acting drugs. With catechol moiety, they correctly resemble with the adrenergic agonist or neurotransmitter of adrenergic system, so they exhibit great activity towards the receptors. Compound without one or both phenolic hydroxyl substitutions are not metabolized by COMT, and they are orally active and have longer duration of action. Because catechol or methyl transferase transfer the methyl group on the hydroxyl group. If this hydroxyl group is not present over there, so the methylation does not takes place and it is not metabolized with the enzyme COMT. So these are the basic SCR points by which we just drive the activity of this adrenergic neurotransmitters or drugs acting on the adrenergic systems. To summarize today's session, we begin with the classification of sympathomimetic drugs based on mechanism of action, receptor selectivity, and chemical moieties. We then study the synthesis of two important agents, that is phenylephrine, an alpha 1 agonist, and salbutamol, a beta 2 agonist. Finally, we explored their structural activity relationship, understanding how slight changes in structure drastically influence drug action. Understanding these aspects is essential in the field of pharmacology, medicinal chemistry, and clinical therapeutics. Thank you for your attention. I hope this lecture gave you a deeper insight into sympathomimetic drugs and their design. For any query or further classification, feel free to reach out on the email or in the comment section. Thank you so much.